Okay, this is a review of radicals, everything that you've ever done, sticking with specifically square roots. Radicals could be cubed roots, fourth roots, fifth roots, but we're working with square roots right now. Simplifying radicals, remember that there are some radicals that are perfect squares. Namely, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 16, 25, 36, missed one, 49, 64. You could go all the way down as far as you wanted. We've got 81, 100, 121, 144. If you know your perfect square, list square root of 25 is 5. If you don't know it very high, always check with your calculator before you try to simplify and find out if that is a perfect square. Square root of 49 is 7. Square root of 144 is 12. But then square root of 20, you know it's going to be partway between 4 and 5, but we don't know the decimal equivalent of it. It's going to be irrational. We can't come up with a terminating decimal. So you were taught probably one way to do it, and that one way was to say, I know a perfect square, 4, that is a factor of 20. So I can break square root of 20 down into the square root of 4 and the square root of 5. I know that the square root of 4 is 2, and the square root of 5 is what I have left. That's okay, and that works. It is a way to do, to simplify radicals. However, there is another way, and I want to show it to you, because for some, it's not easy to come up with the perfect square. They don't have their perfect square list memorized, or it's just not quick in their brain. And another issue is, I know what's coming. I can foresee the future. And in your future, these are not all going to be square roots. They are going to be cubed roots. They are going to be fourth roots. They are going to be fifth roots. And this method won't work because the only thing you're finding is a perfect square. So what are the other options and how are we going to work this out? You can break 20 down into any of its factors. It doesn't have to be a perfect square. I maybe want to break 20 down into 10 and 2. 10 times 2 is 20. Neither one of those are perfect squares. But then I'll break my 10 down into 2 and 5. And you keep going until you are finished breaking it down into all of its prime factors. When I see that I have a pair of 2's, I can say, all right, I can square root that pair of 2's and put that on the outside of the radical and leave my 5 on the inside. Square root of 5 is irrational. Square root of 2 times 2, which is 4, is 2. And some of you right now are looking at that saying, why would I do that? That takes a lot longer. It does, but it also teaches you the right way of how am I going to do this when I have to step it up to the next level. So it's very good practice. Another reason, square root of 32. Okay, maybe don't write this down, just take a look at it. Some people will say, oh, I'll do it the perfect square way. This is the way that I was taught. And I know that 4 is a perfect square of 32. That's a factor. Square root of 4 is 2, and square root of 8 stays in there. And then you get this marked wrong, because this isn't simplified as far as it can possibly go. It is only simplified part way because you found a perfect square, but you didn't find the largest perfect square on the list. The largest perfect square that's a factor of 32 is 16. So it should have been broken down all the way to 4 square root of 2. If you want to, again, void that problem, then just break it down into every factor that you know. 4 and 8, 4 and 2. No sense. I could break this down into 2 and 2 and 2 and 2, but I already have a pair of 4s. When you get to where you have a pair and then a prime number left over, you can stop already. You don't have to continue and take out a pair of 2's and another pair of 2's. As soon as you get a pair, you're allowed to stop. When this is a cubed root, you'd be looking for 3 factors of the same. Square root of 324. Oops. Some of you will take square root of 324 and be like, okay, let's start breaking it down. What goes into 324? And because it's an even number, you know that 2 works. But others of you will grab this handy dandy calculator and say, I better check. I don't want to do all that work and break it all the way down to prime factors unless I know that that's not a perfect square. But the square root of 324 is 18. So there is no need to make a factor tree because it's a whole number. If you don't know if it's a perfect square, check it. Square root of negative 25. Some would say, oh, I got it. It's negative 5. Not true. Not true. The whole idea behind a square root is that you take a number times itself. A number times itself. If you take a negative times a negative, you get a positive 25. If you take a positive times a positive, a number times itself, you get a positive 25. The only possible way you can get a negative 25 is by taking a negative 5 times a positive 5. That's not a number times itself. That's a number times its twin, its evil twin. It's on the other side. This one's on the dark side. Okay? That's not a number times itself. Someday, a couple years, maybe next year, you will work on that with imaginary numbers, but not yet. Instead of calling it imaginary, you can't call it no solution. There is a solution, it's just not a real solution. You can't say undefined, because undefined is reserved for dividing by 0. The square root of negative 25 is not a real answer. And in Algebra 2, you'll find out what kind of answer it actually is. So that's the expected response anytime you try to square root a negative. This is a plus or minus sign. It's a little bit too close together when you type it with a font. Technically, I would say that there would be a space in between them. It could be a positive, it could be a negative. If they want it to be positive and negative, you have to answer positive and negative. 48, check it, make sure it's not a perfect square. I know that it's not because 49 is a perfect square, so 48 can't be a perfect square. I'm going to break it down into any factors that I know. 6 and 8 works, 12 and 4 works, 16 and 3 works, doesn't matter. Keep going until you get a pair or all of your prime numbers. And in this case, I have 2 pair. A pair of 2's, so take a 2 out, and another pair of 2's. The only thing left on the inside is a 3. Take out a 2, don't forget your plus or minus. Take out 1, 2, there's a pair. Take out another, and because these are all factors and this is a factor tree, 2 times 2 is 4. Final answer, positive or negative 4 square root of 3. And you might be thinking, is that right? Did I do that right? Am I supposed to take 2 times 2? Here's how you can check your answer. Square root of 48 is 6.928. 4 times the square root of 3 equals 6.928. You know you didn't change the value of the problem, you just changed the actual look of it. All right, what happens if we have square roots and we have a quotient? We have division. Okay, luckily in these 2 cases, these are the easy ones, they're perfect squares. Don't try to divide 4 by 36. Go ahead and take the square root of 4, which is 2. Take the square root of 36, which is 6. And all rules of fractions, don't even ask, reduce it right away. If it's written as one large number, one large square root, you are allowed to split it up into each of its own divisors. Square root of 1 over square root of 9. The square root of 1 is 1. The square root of 9 is 3. So if you can believe it, those are the same answers. Square root of 4 over square root of 36 is the same value as the square root of 1 over 9. Could I have reduced this first? As long as they're both radicals, you could have. You could have reduced 4/36 first and made it 1/9 and then square rooted it. Sometimes there's 2 options. All right, shifting gears, we're going to now work with squareds. What happens when you square a square root? I'll show you the long cut, and then I'll show you the shortcut. Long cut. Square root of 20 squared says take a number times itself. A square root times a square root is a square root. 20 times 20 is 400. Calculate that out. What is the square root of 400? The square root of 400 is 20. You possibly already see the shortcut. Why do all the multiplication and the simplifying when you know that a square will cancel out a square root? If you square a square root of 20, you're going to get a 20. These are inverse operations. It's just like when we're solving problems. If I add 5 and then I subtract 5, they cancel each other out. If I have multiply by 3 and I divide by 3, they cancel each other out. They're inverses of each other. Adding and subtracting are inverses. Multiplying and dividing are inverses. Squaring and square rooting are inverses. And it doesn't matter which direction you do it. You could square the 25 and make it 625 and then square root, or you could square root of 25 and make it 5 and then square it. It doesn't matter the order. Squaring a square root or square rooting a square will get you right back where you started. So shortcut over here, again, doesn't matter if you square first or if you square root first. A square and a square root are inverses of each other. And do me a favor, please use the word inverses of each other. They're not opposite. It's inverse. Whatever one does, the other one undoes it. It gets rid of it. Okay, enough about those. What happens when you have a whole number and a radical? This is multiplication. Anytime it's multiplication, you don't have to put a symbol in it. I'm going to break down 60 into its factor tree. I'll go with 5 and 2, 2 and 3. I have a pair of 2's. I can take out a pair of 2's, and that's going to go out here outside of the radical. So here's my 2. What's left on the inside? A 5 and a 3. Here, I don't have to squish them in there. A 5 and a 3. So I have a 2. My 60 breaks down into a 2 comes out. 5 times 3 is left over. But don't forget this 3 up here. We were multiplying, so 3 times 2 is 6, square root of 15. Break down the radical, simplify it as you would, multiply the whole numbers. Okay, next. Hang in there. This is a long one because we're covering every radical that we've ever done. Adding and subtracting radicals. They must be like radicals. It's just like variables. I can take a 3x and add it to a 7x, and I know that 3 plus 7 is 10, but I still have x's. I can't take a 3x squared and add it to a 7x because they're not like. I can't take a 3x and add it to a 7y because they are not like. If these radicals are not alike, they do not get added or subtracted. So right now they're not alike, 80 and 320, not even close. But I can simplify each of them and see where we end up. I'm going to go with 4 times 20. I don't know why, I just picked those. And 4 times 5, I might as well pick 4 times 5 instead of 10 times 2 because then I have a pair of 4's right away. 4 square root of 5. I'm going to subtract, hopefully, from 320. I don't know what goes into 320 quickly in my head other than 10, of course, because it ends in 0. I'll break 32 down into 4 and 8. Break my 10 into 2 and 5. I don't have a pair yet, but now I do. I have a pair of 4's, so I take out a 4. I also have a pair of 2's. Please don't count that 8. That 8's been broken down. And my only other dangler, the prime number, is 5. So this says I have 4 square roots of 5, and I want to subtract 4 times 2, which is 8 square roots of 5. Now we have like radicals. Those are alike. They both are square root of 5. What's 4 square root of 5 minus 8 square root of 5? 4 minus 8 is negative 4. And because that's a square root of 5 and that's a square root of 5, this stays as square root of 5. Same as x's. If I had 4x minus 8x, 4x minus 8x is negative 4x. You keep the term, the variable, and just subtract the numbers in front of it. Try it with this one. I'm going to break 65 down into 5 and 13. Oh, 2 prime numbers, 5 and 13. Can't go any further, don't have a pair. Square root of 65 cannot be simplified. The only way we could add these is if they're like terms. I doubt it, doesn't look like they're going to be. Let's break down 72. I'll go into 9 and 8, 3 and 3, 4 and 2, 2 and 2. I have a pair of 2's, I have a pair of 3's. 3 times 2 is 6. What do I have left in the box? A square root of 2. 60, square root of 65 plus 6 square root of 2. You were able to simplify square root of 72, but you're not able to add those because they're not alike. So this becomes your final answer. All right, we added and subtracted. Now we got to do some more multiplying and squaring. If you're multiplying, you can only multiply like, well, I shouldn't say like, the same term. So like a whole number times a whole number. 2 times 5 is 10. And then radicals are allowed to be multiplied. Square root of 2 times the square root of 3 is the square root of 6. So that answer is 10 square root of 6. You do have to be careful and make sure if the 6 can be simplified, you have to simplify it, but that one can't, so that's just your final answer. We already know that the square root of 6 squared, square root of 6 squared is 6. But what happens with 5 square root of 7 squared? You want me to show you what not to do? I can show you what not to do. Don't do this. Oh, a square cancels a square root and you get 5 times 7 is 35. Don't do that. Yes, a square cancels a square root, but there's more happening there than a square root. You have to make sure that that exponent gets applied to the 5 and to the square root of 7. They each need to be squared because the parentheses tells you that. 5 squared is 25 times the square root of 7 squared is 7, and 25 times 7 is 175. Okay, watch this on your calculator. Timeout.
Ms. Vandervan, please call the office. Ms. Vandervan,
Anytime
please call the
that
office.
you have something squared, you're going to get a whole number. It's not going to be a decimal. So, if you type in 5 square root of 7 squared, you're like, yeah, I thought that was wrong. It's not supposed to be 35. That's because you weren't careful on your squared. If you look at what I see there, you see a 5, and then you see a square root of 7 squared. You typed in this. We need to type in this. So you need to start with a parenthesis, then do your 5 square root of 7, but oh boy, most calculators, if you look at that square root button, when they give you a square root, they also give you a parenthesis. So you can't close your parenthesis and then say, oh, 5 square root of 7 squared, because you still get 35. And I'm telling you, the answer is not 35. It's 175. So yes, you can use your calculator, but you got to know how to use it. Left parenthesis, 5, square root of 5, or square root of 7. You see 2 left parentheses, which means you need 2 right parentheses. 2 lefts, 2 rights, 175. Don't rely on your calculator to do the work for you if you don't know how to use your calculator. Square root of 13 times the square root of 26, that's a big number. Take 13 times 26, and you get 338. And you might be like, oh, that's going to be a really big factor tree. I have a hint for you. Sure, you could divide it by 2 and get 169, and then break 169 down. Or you could say, oh, both of those have a factor of 13. So why don't I just break it down right into the tree that I started with? I started with 13 times 26, so why not make 13 times 26? Then I don't even have to think about what else goes into the square root of 338. I have a pair of 13s, and I have a 2 left over. 13 square root of 2. And finally, quotients. So, these are different, but the same, but different than the ones that we did up here, where we had quotients. Can't remember where it was. We had quotients, but they both were perfect squares. Not going to give you all quotients that are perfect squares. So somebody, back in the day, went through the math world and they said, you know what? This is not okay. We can't leave radicals in the denominator. And I'm sure we could Google it or look it up or something, but it probably has something to do with the fact of the equipment that they used abacuses or slide rules or before they had calculators, and it didn't calculate when you divided by a radical. You had to have all radicals in the numerator, none allowed in the denominator. It's like against the math laws. So we have to find a way of getting rid of radicals in the denominator, and we just talked about when you multiply anything times itself, or when you square it, it will cancel the square root. It's the inverse of each other, because the square root of 5 times the square root of 5 is the square root of 25. But what's the square root of 25? The square root of 25 is 5. So we just, what they call it, rationalize the denominator. It's now rational. It's now a whole number instead of a radical. But you can't do that. You can't be like, I'm just going to make that what I want it to be. Rule of fractions, back up quite a few years, whatever you do to the denominator, to keep its value, you must also do to the numerator. So we have 6 times the square root of 5. Since 6/5, if I ignore this, 6/5 is not reducible, cannot be simplified, the square root of 5 cannot be simplified, that's your answer. Okay, so to be honest, this is one of those that I feel like we're in the 21st century now. I don't know that we have to keep rationalizing the denominator, but we actually do. And you'll run into it probably in calc. When to do the math, it's just not gonna work when you have a radical in the denominator. Does this look a lot more simplified than that does? Is this a much more easier to put in a calculator or a computer and calculate it? Yes. But is it simplified? No. Rationalize the denominator. You might want to write that, because you will hear it called that. Rationalize the denominator. And it sounds like you're super smart when they say, what'd you do in math today? And you say, oh, we found X. What'd you do in math today? We rationalized the denominator. It just sounds like you're really high level. All right, when they're both radicals, first try to simplify them. Take 32 divided by 3. Can't. That didn't work. Not a whole number. So we are still going to have to rationalize it. Multiply by square root of 3 so that you have a 3 in the denominator. Multiply by square root of 3 up here. 32 times 3, they're both square roots. You get 96. The square root of 96 over 3. But you got to check it. It looks like, oh, okay, that's not so bad. But does the square root of 96, can we make a factor tree out of that and simplify it? I'm going to go with 3 and 32, just because I know that those two work. You don't have to. I'll break 32 down into 16 and 2, and I'll break 16 down into 4 and 4, just so I have my pair of 4s. I have a pair of 4s. What's left is a 3 times 2, so I have 4 square root of 6 all over 3. This is simplified. More than square root of 32 over 3 and more than square root of 96 over 3. That's what a simplified fraction looks like. Everything is reduced, everything is broken down. 4 left. I've got to show you these because you got to see them. Square root of 6, square root of 3. Oh, I can reduce those before I rationalize them. 3/6 can reduce to 1/2. So now my fraction looks like 2 over square root of 2, much easier to work with. What happened to this square root? It was a 1. What's the square root of 1? 1. What's 2 times 1? 2. So anytime you can reduce a fraction, we tried to with 32 over 3, but it didn't work. But 3/6 works. Now the rationalization is a little bit quicker. Multiply by square root of 2. In the denominator, you have a 2. In the numerator, you have a 2 on the outside and a 2 on the inside. Take a look at that fraction. Cover up your radical. 2, 2. 2 halves. 2 over 2 reduces to 1. And your final answer is square root of 2. And so help me, if you put a 1 in front of your radical, don't put a 1 in front of your radical. I already know there's 1 square root of 2 there. You don't have to tell me there's 1 square root of 2 there. It's just like an x. Leave it. Square root of 2 is your final answer. And lastly, no, maybe not lastly, square root of 10 over square root of 2. 10 divided by 2 is 5. You can do that because they're both radicals. Your final answer is square root of 5 because it doesn't simplify and there was no denominator. Would you have gotten there eventually? Oh yeah. Skip this part if you don't even want to see it. You could have rationalized it and gotten the square root of 20 over 2. But then you would have had to break down 20 and you would have eventually ended up with 2 over square root of 5, 2 square root of 5. And then you would have got a 2, and then you would have reduced it, and then you would have got a 5. So if you get in the mode of like, I have to rationalize the denominator, rationalize, you would get there, but why don't you simplify it first? 10 divided by 2 is 5. Just think, work smarter, not harder. Here's another one. You could rationalize this if you want to take 75 times 50, but you could reduce it first. The square root of 50 over the square root of 75. You got 2 quarters up there, and you got 3 quarters down here. I always go by quarters when you talk about 75 because I know my money. Okay, so 50 cents, 75 cents, 2, 3. Much easier numbers to work with. Much less simplifying. The square root of 2 times the square root of 3 is the square root of 6. The square root of 3 times the square root of 3 is 3. Do not reduce that. You can't simplify that. You see 6/3 and you're like, 2, I know this. 6/3, that's 2. 6 divided by 3. One's a radical, one is not a radical. Can't mix them. Leave it as is. Final one. 6 over square root of 8. I'm going to move it down here so we have room. Rationalize it. You can't reduce 6 over 8 because they're both not radicals. You get 6 square root of 8 over 8. There's going to be a lot of work to do here. Bear with me. We're going fast. 8 breaks up into 4 times 2. 4 breaks up into 2 times 2. You end up with 2 square roots of 2. By the way, that's one that you really should memorize. Square root of 8 is 2 square root of 2. We use it a lot. But you have this 6 times that 2. So our numerator is actually 12 square root of 2 over 8. But then you cover up this square root of 2 and you see 12 eighths. And you know that 12 eighths are both divisible by 4. So you have a 3 there and a 2 there. So not only did you have to rationalize it, first rationalize it, then simplify the radical, then reduce the fraction. 3 steps in one. That's your final answer. Holy cow, that's a lot of notes, but that's what radical review looks like. Good luck.